Hi, this is Mark Zoback at Stanford University. I guess you're seeing this because it's the backup and there's been some glitch in my presenting live, but I hope you enjoyed the presentation and it's nice to be talking to you today. I'm going to share my screen here and we'll get started. Title of my talk, it's a little bit strange. This is not really a scientific talk. I'll make some scientific points. But this talk is based on a talk I gave for the SPE, the Society of Petroleum Engineers, and Ray thought it would be of interest to this audience, and I hope you enjoy my comments. I think we all recognize that the need to decarbonize the world energy system is beyond dispute. The scientific evidence is overwhelming. This particular slide shows that if we hope to not exceed the 2 degrees C limit by near the end of the century, we need to be reducing carbon emissions by about 4% on a year-on-year basis. That's a big number, actually, when you consider that it has to be sustained every year for the next half century. But, if we do all the right things and we get started, perhaps it's achievable. And the need to do this is overwhelming. Perhaps it was a little more important to talk to the Society of Petroleum Engineers about this than it is to the audience at this meeting. But this was just last year. In case we've forgotten, record-setting temperatures throughout much of the southern and southeastern United States in October, temperatures approaching or reaching 100 degrees Fahrenheit in the autumn. We know what's driving global warming. It's CO2 and methane in the atmosphere, as you've heard from the previous speakers. And we know where the CO2 is coming from. It's coming from making electricity and providing heat. It's coming from transportation. It's coming from manufacturing and construction. And it's coming from a number of other sources. This slide is roughly the last 30 years or so of data. And we know that when we talk about electricity and we look at a global basis, and stationary energy needs for electricity and needs for heat from industry, coal is the dominant source of energy. And when we talk about oil, for example, we're principally talking about transportation. That's especially true in the US and the developed world, but it's true almost everywhere. Now, what I'm not talking about today is some of the things you already know. You already know that we're rapidly starting to convert cars and light-duty trucks to zero-emission vehicles, electric vehicles. It's well underway. But there are currently 1.5 billion cars in the world, and they last about 11 years. And it's going to be quite an effort to replace that inventory. In California, there are about 600,000 electric vehicles, about 4% of the total cars on the road. The state goal is to have about 5 million on the road by 2030. There's about 15 million cars now. And that's going to require a 25% increase year on year. It's extremely ambitious. I'm doing my part. I just love driving my Tesla. But hydrocarbons are going to be needed for a long period of time, even in places like California, which have a very aggressive decarbonization goals. You also know that oil and gas, principally oil, is going to be needed because we now have, no viable low carbon transportation fuels for aviation or heavy duty trucks and vehicles. Maybe it's going to be hydrogen fuel cells. Of course, we're all talking about blue hydrogen, which comes from methane, eventually going to green hydrogen, which, say, through electrolysis, not producing any CO2, but at least in the near term, we're going to be producing CO2 even if we go to hydrogen. Biofuels are, they've been talked about for a long time, but they really haven't penetrated the market. Can electric vehicles function in heavy-duty trucks? Can they function in aircraft? It's looking doubtful, but hope springs eternal. So hydrocarbons are going to be needed for decades to come for aviation and heavy-duty transportation. And finally, we have 40 gigawatts of natural gas electrical power generation in California, and we have 20 gigawatts of renewable electrical power generation, mostly solar, but a lot of wind as well. The problem is it's mostly sunny and it's mostly windy in the summertime. And if you actually look at the utilization factor of this 20 gigawatts, it's very low. It's only about 3 gigawatts. So you kind of have to overbuild, and there's no backup. There's no backup at night, and there's no backup when the wind is not blowing. And so a logical backup for an increasingly renewable electrical energy sector would be natural gas and or hydrogen. But right now, that's ruled out of state mandates that we have. There's a renewability, standard in place in addition to decarbonization standards. So I don't think this is going to be achievable without natural gas as a backup. I think natural gas is the natural partner for renewables, and you can't have one without another until there are viable backups and power can be generated 24/7. Okay, so what am I going to talk about? I want to talk about the unconventional revolution and the new abundance of natural gas, because it provides immediate opportunities for decarbonization of the global electrical power sector. It's already underway in the US, but it can happen globally. The unconventional revolution isn't over. In fact, I'd argue it's just begun. There's tremendous opportunity to do better than we've done. The new abundance of natural gas can address the pressing need for a thermal fuel in the developing world. Till very recently, this was really overlooked as a goal for international development. And the most important part of this message has to do with CO2 sequestration and the fact that the oil and gas industry must be part of the solution and not just part of the problem. It must play a major role in reaching CO2 emission reduction standard, to achieve the objectives of the Paris Accords. So let's go. You know about the unconventional gas revolution, the tremendous increases of natural gas, even at very low prices. That's been achieved in a little bit more than a decade. This graph is for the United States and broken down by different unconventional basins. And the result of fuel switching, turning off coal-burning power plants and replacing coal with natural gas has resulted in a dramatic decrease in CO2 emissions from the electrical power sector. There's simply no question that it works and it's economically viable. But in the future, the increase in CO2 emissions is not going to be coming from OECD countries. It's going to become from non-OECD countries. Okay, and I want to just throw a number at you. If the remaining coal generating capacity in the United States is around 300 gigawatts. Okay, now let me put that in perspective. But first, we all recognize that economic development requires energy, and this graph appears in many different forms. The countries are shown by population, and its energy use per capita on the x-axis and gross national income per capita on the y-axis. And for economic growth, we need energy, and we need reliable energy. We need energy that's available 24/7, but we need that energy to be as low carbon as possible. We need that energy to be as non-polluting as possible in order to promote economic development around the world. So 300 gigawatts is producing about 70% of our emissions. Coal is the culprit. But what does 300 gigawatts mean globally? Well, this puts coal in a bit of a perspective, because the yellow is when this slide was prepared. This is the operating capacity. The light purple color here was under construction, and the dark purple is proposed. Well, 300 gigawatts is, and the gray is decommissioning. 300 gigawatts is what's shown kind of by that dashed line. And you can see that, the entire coal capacity of the United States is offset, but by what's under construction in more or less in a single year in the developing world. And so the reality of the situation is what's happening outside the United States, and can we promote fuel switching outside the United States? Well, why isn't it happening? Well, it's not happening because in general, coal is the cheapest alternative. But as Mark Thurber, an economist at Stanford, has pointed out, that if you look at India, for example, and you say, coal is, $2.7 per million BTU, and LNG is costing $7. People choose coal because it's cheaper. But in fact, the very small price on carbon, $22 a ton, would actually switch that and make coal more expensive. If you put a price on the health effects, the pollution effects, of carbon, of burning coal, that would tilt the balance. And things are not out as far out of reach as possible. And frankly, in the global downturn associated with the COVID-19 pandemic, the difference between these numbers has gotten smaller because gas has gotten cheaper. And perhaps a silver lining might be enhanced use of natural gas in the developing world. The pollution issues associated with coal is a serious issue. The number of premature deaths estimated to be 366,000 in China in 2013, roughly 100,000 in India at about the same time period. Let's talk about the unconventional revolution. Gas prices, oil and gas prices are down. The level of activity in the unconventional basins in the United States is way down, and it's easy to be pessimistic. The industry is awash in debt, but I'm quite optimistic. And the reason I'm quite optimistic is because there's so much hydrocarbon left behind, and we've done such a poor job of getting it out. There's a very large opportunity for improvement. Now, the basic strategy, as all of you probably know, is to drill horizontal wells. You conceptually drill them in the direction of the minimum horizontal stress, and when you hydraulically fracture them in stages, you get hydraulic fractures propagating perpendicular to the well path. You put the wells close to each other, and you stimulate the area in between the wells and produce from this footprint. The little tick marks represent small micro-earthquakes. Those micro-earthquakes represent slip on pre-existing faults due to the leakage of pressure out of the hydraulic fractures. So these dots represent microseismic events. Over here in this simulation, the blue is hydraulic fractures. The little discs here are, in fact, these microseismic events, which we've determined the size and the orientation of the planes that are slipping. It's a bit of a long story, but what we see conceptually in this cartoon is, so this is half realization and half data. Now, how well do? We do pretty badly. This is from a recent paper. It's also in a recent book I've written on unconventional reservoir geomechanics. On the left is the Eagle Ford play in Texas, the Bakken in North Dakota, the Barnett in northeastern Texas, and the Marcellus, West Virginia, Pennsylvania, and a little bit of Ohio. What you can see, each of these lines represents 2 years and hundreds to thousands of wells, and the production rate from these wells declines very fast, okay? In each and every case. Doesn't matter if it's oil, which is the Eagle Ford and the Bakken, or natural gas, the Barnett and the Marcellus. The production rates decline very rapidly with time. The cumulative production is shown over here. And what you see is, on a well-to-well basis, there's been about a 40 to 50% increase in most of these plays, there's been about 100% increase. The methodology that's used in the Marcellus has improved dramatically. But the economics are complicated. They're complicated by fluctuations in the price of oil and gas, of course. Operational efficiency has improved remarkably, and the level of effort has improved. And so some of this increase that we see from the old wells to the new wells is due to the fact that we're just trying harder. The wells are longer, there's more hydraulic fracturing, there's more fluid, there's more proppant put into the hydraulic fractures. To illustrate that, this is a recent paper. This was an undergraduate research project at Stanford. Irfan Rostami presented it at the ERTEC meeting in July. And here's the data for the Bakken. And what it shows is, as time has gone on, the more recent epochs are these 2-year periods we broke the data into, the average per well has gone up, as I described in the previous slide. But the wells have also gotten longer. And if you actually correct for the length of the wells, what you see is the production per foot of well has actually gone down. And so we're working harder to achieve this, but we're not working smarter. We're actually getting less proportionately for a given amount of effort. And so after 200,000 wells or so in the United States, the recovery factor for dry gas is about 25%. The recovery factor for tight oil is about 2 to 10%, and there are many uneconomic wells. So this industry, when you're thinking about gas and we're thinking about oil especially, the great majority of the hydrocarbons is left behind. And I think there's a tremendous opportunity for improvement. Just to give you a sense of the size of the industry, the expenditures for drilling and completion in the United States in 2018 were almost $80 billion. A lot of money is being spent, and we're leaving more than 90% of the oil behind. And there's potential around the world. This slide is a little old. The Vaca Muerta here in Argentina is going great guns. China is moving fast. But other places, Europe, of course, has great opposition to all this and probably will never realize development of their resources. Australia is a battleground. There's very strong support in some parts of Australia and very strong opposition in others. Nonetheless, there are unconventional resources essentially everywhere there's oil and gas produced. So what does this mean? It means that natural gas and natural gas liquids can address the pressing need for a thermal fuel in the developing world. And we all know what energy poverty looks like, the billions of people who have no access to electricity or any source of heat or cooking fuel, that every day are gathering sticks and dung just to get through the day, the hours of drudgery that are associated with this, and the health effects. This is a picture from the Pamir Mountains, far western China near Tajikistan, in Kyrgyzstan. That my wife or I took this picture. It's at about 14,000 feet. It's a summer, temporary village that the sheep and yak herders use. And so what you can see here is some solar panels. You can see a satellite dish. This is pretty cool. These are shepherds in a very remote area, and they have solar panels, and they actually have a connectivity to the outside world. But their only source of heat, their only source of cooking is to burn dung. And it turns out that 3 to 4 million people per year are dying due to indoor air pollution. This is an estimate of the World Health Organization. And that is more than AIDS, malaria, and tuberculosis combined. And the answer to that is basically natural gas and natural gas liquids. And we're seeing a great progress. India's had a major program for distributing propane in remote areas for cooking and heat, and other places are as well. And so it really should not be overlooked, the importance of these resources. Finally, let me focus on CO2 sequestration and the role of the oil and gas industry. I want to start by talking about the some estimates from the OGCI, which is 15 major companies from around the world. Until 2018. They were non-American companies. 3 American companies, American-based companies, joined in 2018. Now this is CO2 captured and stored as a function of time out to 2060. OGCI is basically using the IEA perspectives, and I've just used their graphic here. The sources of the CO2 are shown here by the different colors. Now this is what is needed from CCUS. Now we need to use multiple strategies to decarbonize the energy system, but this is from carbon capture and storage. Now this looks like a cumulative plot, but it is not. It is the amount of CO2 in gigatons per year, billions of tons, that needs to be captured and stored each year as we go forward. Okay, so where are we today? We're currently storing about 30 million tons of anthropogenic CO2 per year. We're not even off of the thickness of the black line. Where do we need to be as we look 15 to 20 years out? Well, the number is pretty big. It's 3.4 or so gigatons of carbon CO2 per year. What does this number mean, 3.4 gigatons of CO2? Well, in the subsurface, under reservoir conditions, CO2 is supercritical. It's more like a liquid than a gas. If we think of it as terms of a volume of supercritical CO2, 3.4 gigatons of CO2 converts to 30 billion barrels. What is 30 billion barrels? 30 billion barrels is the size, roughly, of the current oil and gas production, distribution, and consumption industry. So you can't get your head around what 3.4 gigatons of carbon means, but you have some idea of what the infrastructure is that we're talking about. There's 1 million wells, there's hundreds of thousands of kilometers of pipelines, there's hundreds and hundreds of distribution centers, and so on. It's an enormous undertaking, and that's where we've got to be by 2040, 20 years to build something on the scale of the global oil industry, but going the other way, storing supercritical CO2 in the subsurface. By 2060, we have to be at twice that scale. The shell sky scenario, if any of you have heard of that, it's an all of the above strategy, all the different things you have to do. But the role for CO2 sequestration is very, very similar to the IEA and the OGCI estimates. About a gigaton of CO2, not long after 2030, 1.5 times global oil production by mid-century, while we're doing many other things as well. Now, there's nothing new about the idea of geologic storage of CO2. This is from 2005, the IPCC report, and multiple strategies of different kinds of geologic formations that could be considered. The US and the academic and research community is largely focused on saline aquifers for storage of CO2, but there's tremendous challenges. The time to develop these saline aquifers can be many decades. There's always strong public opposition, numerous stakeholders. The costs are enormous. Issues of liability and regulations for monitoring and potential remediation haven't been worked out, and so on. And there's geologic challenges. The pore space is not empty. The pores in the rock are occupied by brine, and the required volumes can result in significant pressure increases over very large areas. However, massive injection of CO2 into depleted oil and gas reservoirs, can occur. And I think it's the only realistic pathway to significantly reduce carbon emissions. Remember, everything we do in this decarbonization strategy, in general, makes the rate of carbon accumulation in the atmosphere go down. Sequestration of CO2 is the only thing that makes the absolute numbers go down. We're not just emitting at a lower rate, we're actually lowering. It's a negative emission strategy. So there's existing knowledge of the subsurface. There's much infrastructure already in place. New infrastructure will be required. The pore space to accommodate these enormous volumes are being produced, every year when we produce the oil. In other words, we have a lot of pore space in the bank because we've been, producing this equivalent for 3.5 gigatons of CO2 every year as we go back in time. And there's a potential positive impact on production that is often emphasized, but I think that's really not the issue. I think the real issue is how we're going to store massive amounts of CO2, whether or not we co-produce oil in the process. I think it may, in fact, be more palatable not to be producing oil and just storing carbon, to make it absolutely clear that the oil and gas industry is part of the solution here and not trying to simply perpetuate the oil and gas industry in a lower carbon world. So, to me at least, my vision for the oil and gas industry in the era of decarbonization, the oil industry in the future, is one in which oil companies, oil service companies, the oil industry is equally engaged in continuing to produce oil and gas as it's needed. As I began my talk, we're going to need oil and gas for many years into the future, despite the fact that we might not like to when we consider the need for decarbonization. But the industry also needs to lead the way, needs to be in the business of sequestering enormous quantities of CO2 in depleted oil and gas reservoirs, if in fact we're going to meet this global decarbonization challenge. Thank you very much.